four closed surfaces, S1 through S4, together with the charges minus 2q, q, and minus q are sketched in the figure below. The colored lines are the intersections of the surfaces with the page. Find the electric flux through each surface. So what we have to know here. So remember that the electric flux through any surface will be equal to the Q interior over epsilon sub 0. Let's analyze the surface S sub 1. And I will just highlight, just put it in red, the surface S sub 1. So S sub 1 is this surface over here. And then when you look at the charges that we have inside, we have one charge plus Q, and we have one charge minus 2Q, all divided by epsilon sub 0. Plus Q minus 2Q is going to be minus Q over epsilon sub 0. So to the surface S1, the electric flux, that is Q interior over epsilon sub 0 over the permittivity of the free space, is Q minus 2Q, because these are the two charges that are enclosed by surface 1, which is minus Q over epsilon sub 0. Studies. Now, let's erase the red line that I did to highlight the surface S1, and let's highlight the surface S sub 2 now. Now let's see what is S sub 2. S sub 2 is this surface. So we just highlight in red S sub 2. So this is S sub 2. So the electric flux through S sub 2 is also the Q interior, so the net charge inside the surface, divided by the permittivity of free space. Now, what charges we have inside this surface? Plus Q minus Q, divided by epsilon sub 0. Plus Q minus Q, that is 0 over epsilon sub 0. So this is 0. So the net electric flux through the surface S sub 2 is equal to 0. The next electric flux to the surface S sub 2 is equal to 0. Let's do the same now with S sub 3. Let's do the same with S sub 3. So I will highlight now in red S sub 3. S sub 3 is this bit area, or this bit surface. And then let's see which are the charges inside the surface S sub 3. So we know that the electric flux is equal to Q interior. So we know that the electric flux is equal to Q interior over epsilon sub 0. Now, what is Q interior here? We have minus Q plus Q minus 2Q over epsilon sub 0. Now what happens? That we have that minus Q and plus Q cancel out. So we get minus 2Q over epsilon sub 0. Minus 2Q over epsilon sub 0. This is, the electric flux to the surface S sub 3. Because always we calculate the electric flux regardless of the shape of the surface as Q interior or epsilon sub 0. Now, let's find the last. The last one is through S4. And we highlight in red S4. And as you can see here, S4 doesn't contain any charge inside. So when you go over S4, then you have Q interior over epsilon sub 0, Q interior is 0. Why? Because no charge is in S4. So the electric flux will be 0. There is a difference between the electric flux equal to 0 in case 2 versus the electric flux equal to 0 in case 4. In this second case, for the surface S sub 2, the electric flux was 0 because we have two charges with opposite signs, plus Q and minus Q, and they cancel each other. In the second case, for the surface S sub 4, it's because we don't have any charge inside. So if we don't have any charge inside, Q interior is 0, because Q interior is the sum of all the charges inside. So we have no charge inside, Q interior is 0. So this is one example of an exercise, that we can solve about these, for example, Gaussian surfaces. They say in this exercise, the following charges are located inside a submarine. Are located inside a submarine. And the charges are 5.00 microcoulomb, minus 9.00 microcoulomb, 27.0 microcoulomb, and minus 84.0 microcoulomb. So they say calculate the net electric flux through the submarine MB is the number of electric field lines leaving the submarine is the number of electric field lines leaving the submarine greater than or equal the number entering up greater than or equal the number entering off. So let's try to understand what is going on here. So we have the submarine, and we have here one positive charge, okay, of 5.00 microcoulombs. We have one negative charge of minus 9.00 microcoulomb, right? It's going to be here that charge. We have another charge of 27 microcoulomb positive. And we have another one here that is negative 84. Yeah, and we have this other of minus 84.0 microcoulomb. So we have to calculate the electric flux to the submarine. Well, we know that this electric flux is Q interior over epsilon sub 0. And Q interior would be 5 microcoulombs. Now remember that 1 microcoulomb is the same that 1 times 10 to the negative 6 coulombs. We always have to work with coulombs. We cannot work with micro, with nano, with milli. We have to work with coulombs. So we say that this is 5.00 times 10 to the negative 7 times 10 to the negative 6 coulombs. This is the positive one. And later minus 9.00 times 10 to the negative 6 coulombs plus 27.00, sorry, 0.0 times 10 to the minus 6.00, sorry, 0.0 times 10 to the minus 6 coulombs plus, in this case, minus 84.0 times 10 to the negative 6 coulomb. All this divided by epsilon sub 0. And epsilon sub 0 is 8.8542 times 10 to the negative 12 Coulomb square over Newton meter square. Well, when you find this Q interior, 5 minus 9 plus 27 minus 84, that would be minus 61.0 times 10 to the negative 6 coulombs, all divided by 8.8542 times 10 to the negative 12 Coulomb square over Newton meter square. Now, when you find the electric flux, it's going to be negative, and it's 6.89 times 10 to the 6 newtons meter square per coulomb. So when we divide the negative 61.0 times 10 to the negative 6 by the 8.8542 times 10 to the negative 12, it gives us the minus 6.89 times 10 to the 6 Newton meter square per coulomb. And this is the electric flux. This is the electric flux, you know, that cross or that pass through the area, through the surface area of the submarine. Now, there is one question here that to understand, you know, what is this about, we have to recall what happened with a charge that have a negative sign. When you have a charge with negative sign, remember that the electric field lines point toward the charge. And when you have a positive charge, remember that the electric field lines points outward, so points leaving the electric charge, right? And leaving the electric charge. So, due to the positive charges, there will be electric field lines leaving the submarine, right? And due to the negative charges, there will be electric field lines that are entering into the submarine. Remember, in the electric field charges that are negative, the electric field lines, sorry, when we have negative charges, the electric field lines point toward the charge. When the charge is positive, the electric field lines points leaving the charge. Now, what happens? In Gaussian surfaces, we consider that the electric field lines that go from out to in when the electric field lines go from out to in, the electric flux is negative. And the explanation is simple. The explanation is because the normal vector here always point outward. So the angle between the normal vector and the electric field vector is 180 degrees. And the cosine of 180 degrees is -1. Now, so when the electric field lines go from out to in, the electric flux is negative. When the electric field lines go from in to out, like this, the electric flux is positive, and it makes sense because now the angle between the normal to the surface and the electric field is 0 degrees, and the cosine of 0 is +1. So it makes sense that the electric flux be positive when the lines are going out. Now, what is the problem here? We have that the net charge inside is minus 6.89 times 10 to the 6. Sorry, this is the electric flux, negative. So we have an electric flux. Let me just represent this a little bit different. We have in the net charge, the interior net charge is negative 61.0 times 10 to the -6 coulombs. This is the Q interior net. And we got an electric flux that is negative. So if the electric flux is negative, it's because there are more lines going in that line is going out because the electric flux that we got is negative. So the negative electric flux is because the Q inside, the Q interior is negative. So the negative electric flux is because the Q inside, the Q interior is negative. So the lines go from outside to inside. The electric field lines go from outside to inside. And when the electric field lines go from outside to inside, they are going against the direction of the normal to the surface, and then the angle is 180 degrees, and the cosine of 180 is -1. No, the cosine of 180 is -1, and then the electric flux is negative. So we can say in this case, you know, that there are more lines entering, and there are less lines leaving the submarine. So less electric field lines are leaving the submarine and entering the submarine. And entering. Now, before analyzing these problems, right, with the Gauss law, we were talking about the definition of electric flux. And we said that the electric flux is the amount of electric field lines, is a measure of the number of electric field lines that pass through a given area, right? So I would like to show you now another problem before moving to another topic that is about the electric potential. And the lab practice we have today is about electric potential. So before doing that, I would like then to move to show you one more exercise. May I change the slide? So let me go back to where I was sharing the files. And then let me show you one problem. It's this one. And in this problem, look at this. They say an electric field of intensity 3.50 kilonewtons per coulomb is applied along the x-axis. So calculate the electric flux through a rectangular plane, 0.350 meters wide and 0.700 meters long, if the plane is parallel to the YZ plane, the plane is parallel to the XY plane, and the plane contains the y-axis and its normal, makes an angle of 40 degrees with the x-axis. So remember that we mentioned that the electric flux, is equals to the electric field times the area times the cosine of theta. And basically what we said was this. We said we have an area this area have a vector perpendicular to it that is called the normal vector. And then we have these electric field lines that make some angle with respect to that normal vector. And this angle between the normal vector and the electric field is what we call zeta. That was what we explained. Now, what they give us in this problem, they give us the dimensions of the area. They say that their plane is a rectangular plane with dimensions 0.700 meters of length, and the width is 0.350 meters. So if I want to find the area, that is all this amount of surface we have over here, it's L times W. So it's 0.700 meters and 0.350 meters, which is then 0.245 meters squared. So once I know the area, now we're ready to calculate the electric flux for the different position of the plane. Why? Look at this. How do you represent a three-axis coordinate system? That means a three-dimensional coordinate system. You have here y, of course. This is x. And then this is the axis z. Now, when the plane is in the is parallel to the YZ plane. The YZ plane is this plane over here. So a plane parallel to the YZ plane is going to be a plane that is going to be like this. This is a plane parallel to the YZ plane. Now, the electric field is in the direction of the positive x-axis, or on the x-axis. So the electric field is like this. And it's 3.50 kilonewton per coulomb. Now, the normal to the plane is in the same direction that the electric field. So the angle theta between the electric field and the normal is 0 degrees. And the cosine of 0 degrees is 1. So when I know that electric flux is EA cosine of theta, since this is 1, the electric flux in this case would be E times A. In this case would be E times A. So the electric flux in this case will be E, that is 3.50 kilonewton. So kilo is 10 to the negative 3. So times 10 to the negative 3 newtons per coulomb times the area that we found is 0.245 meters squared. So we find that the electric flux here is equal to 858 newtons meter square per coulomb square. And this is the maximum electric flux that passes through that area. This plane in green that you see is parallel to the YZ plane. It's parallel to the YZ plane. So it's perpendicular to the x-axis, so it's perpendicular to the electric field. But the normal to that plane is parallel to the electric field, and the angle is not between the plane and the electric field. The angle is between the normal to the plane and the electric field. Now, in the second case, we have the same thing. X, Y, and Z. Again, we have our electric field in the direction of the x-axis. But now my plane is in the xy plane, parallel to the xy plane. So when you are parallel to the xy plane, the plane is like this. The normal to that plane would be a point, would be a dot. What you see instead of the arrow would be like a kind of dot. And the electric field lines are like this. So what happens? That these electric field lines and this normal that is leaving the plane of the screen, of the computer, the plane of the board, the plane of the screen, the angle between the normal and the field is 90 degrees. And the cosine of 90 degrees is 0. So when we say, oh, I know that the electric field the electric flux is equal to the electric field times the area times the cosine of theta. Since here theta is 90 and the cosine of 90 is 0, all this expression becomes 0, and the electric flux there is 0. So when the plane, when the plane is parallel to the electric field, or the normal to the plane is perpendicular to the electric field, the electric flux is 0. The electric flux is 0. And then finally, we have the third case. In the third case, we have that there will be some angle. So what we have is now one plane that will be like this, because it's a sun angle, with a normal that will be like this, and with a field that will be like this. And this one is the angle theta. And now this angle between the field and the normal to the plane is 40 degrees. So you can say that the electric flux is equals to EA cosine of theta. So it's E, that is 3.50 times 10 to the negative 3 newtons per coulomb, and the area 0.245 meters squared times the cosine of 40 degrees. And then the electric flux in this case would be equal to 657 newtons meter square per coulomb square. And there we have the values. Now, let me try to explain you quickly. What happens with the electric flux? I have here a piece of paper. This would be the plane. When the plane is perpendicular, my plane would be the electric field lines. When the plane is perpendicular to the electric field lines, we have more area. We have the maximum area here facing the electric field lines. So basically, the electric flux is this. Are lines that are crossing through this plane, right? This is the electric flux. Lines crossing the plane. So the normal, imagine the normal is an imaginary line perpendicular to the plane. Sorry, yeah, perpendicular to the plane. So when the plane and the electric field line, this blue is the electric field line. When the plane and the electric field line have an angle of 90 degrees, the normal, that is an imaginary line in this direction, is parallel to this. And that's why the angle is 0, and the cosine of 0 is 1. That's why the electric flux is maximum. But the electric flux is maximum basically because you have more area facing the electric field lines. Now, if now my lines and my plane are parallel, there is no way that the lines be crossing through the plane. This is the plane, right? It's this second case. The first case is this, right? This is the first case. This is my plane, this is my field lines. The second case, case B, is this. Plane in this plane, xy, and the electric field lines along the x-axis. Electric field lines will be parallel to the plane. They are not crossing to the plane. There is electric flux only if the lines cross to the plane. Now, what is the third case? It's not perpendicular, it's not parallel. There is some angle. The problem is that when there is some angle, the area facing the electric field lines is smaller, right? The more area is when you have this plane perpendicular to the lines. But if now I put the plane like that, only a few lines are going to be able, as more I incline the plane in that direction, less area facing the plane, so less area available to have electric field lines closing to that area. So that's why this is the intermediate case. No, when there is some angle. Now remember that always the angle that we're talking about, let me show you something. The angle we're talking about, right, is not this angle between the plane and the line. When the angle is different of 90 degrees, it's not this angle. This is the line, this is the plane. The angle is not this angle. It's the angle between this electric field line and the line that is perpendicular to the normal. So if they give you this angle between the plane and the electric field line, and you want to find the angle theta, that is the angle between the plane, between the normal to the plane and the electric field line, you must subtract this angle from 90 degrees to find this angle. So it's confusing, but yeah, with some reading these multiple times and trying to represent, the problem in your mind, you will be able to eventually, just understand this, right? Now,